I'm talking about the Intel 8086 microprocessor. It's basically the 16-bit grandfather of modern computing. It literally laid the architectural foundation for the very device you're probably using to listen to this explainer right now. And what makes the 8086 an absolute marvel of engineering isn't just what it could compute, but how it managed to pull the whole thing off with an incredibly tight physical footprint. So we're going to explore this microprocessor today as if it were a highly efficient, tightly orchestrated factory.
40. They had exactly 40 physical pins. No more, no less. And they had to orchestrate an entire complex computer system with just those 40. Every single piece of data, every memory address, every command, every power source, it all had to route through just 40 tiny metal legs. That means every single one of those pins had to be assigned a completely flawless role. I mean, how do you even run a massive computing factory with only 40 doors in and out?
Well, here's our factory tour map. First, we'll cover the base utilities and factory foundation, then the shipping lanes and multiplexing hacks, move on to the traffic lights of system flow, look at emergency alarms and interrupt signals, compare the minimum versus maximum mode foreman, and finally wrap up with the 40-pin architectural legacy. Okay, Section 1. Base utilities and factory foundation. So before any real work gets done, our little silicon factory obviously needs the basics just to keep the lights on and the workers in perfect sync. First up, we've got VCC providing a steady plus 5 volts of power, and not one, but 2 GND pins acting as our 0-volt ground reference to handle the electrical load. But power isn't enough on its own. A factory needs a rhythm, right? That is exactly where the CLK, or clock pin, comes in. You can think of this as the factory metronome. Depending on your specific version of the chip, this single pin gets a steady pulse at 5, 8, or 10 megahertz, and that perfectly synchronizes every single internal operation. Finally, we have the reset pin. When this active high pin gets triggered, it basically initializes the whole processor, completely clears out the instruction queue, and forces the chip to start executing code from a very specific location, FFF0H. Hits quite literally the ultimate fresh start button. Moving right along to Section 2, shipping lanes and multiplexing hacks. Now, this is where things get really fascinating, mostly because of a major mathematical headache the engineers had to solve. Here's the big challenge. The 8086 needs to process 16 bits of data at a time, and it needs to point to memory addresses that are 20 bits long. Well, if you do the math, 16 plus 20 means you'd need 36 pins just for shipping materials. And remember, we only have a strict 40-pin budget for the whole shebang. There is simply no way that works while leaving any room for power and control. So the brilliant solution here is multiplexing. It's an incredibly clever engineering hack. Think of it kind of like a reversible commuter lane on a busy highway. Multiplexing lets you use the exact same physical doors for completely different traffic, just on a very strict schedule, instead of having to build entirely separate doors. Take pins AD0 through AD15 as a prime example of this. During the very first clock cycle, which is known as T1, these 16 pins essentially shout out a memory location. They're carrying the lower 16 bits of the address, from A0 to A15. But right after T1, for all the remaining clock cycles, their job completely changes. They just magically switch over to transmitting or receiving the actual 16-bit data, D0 through D15. It is such an incredible time and space-saving maneuver. And to hit that full 20-bit address requirement, we've got pins A16S3 through A19S6. During that same T1 cycle, these guys carry the upper 4 bits of the address. But then, after T1, they swap over to outputting status signals, basically telling the rest of the system which memory segment is currently being accessed. We also have the BHE/S7 pin, which enables transfers through the upper half of the data bus. That's super vital for accessing odd memory locations. But wait, here's the catch. If a pin is acting as an address for a microsecond and then data the very next, how does the rest of the computer not get completely confused? Well, that is the job of the ALE pin, or address latch enable. When ALE fires, it signals an external latch to basically grab the address and hold onto it, so the processor can safely switch the pins over to data mode. Without ALE pulling them apart, the whole factory would just break down in total confusion. All right, onto Section 3, traffic lights of system flow. So we have our multiplexed shipping lanes, but we definitely need strict control signals to dictate exactly what operations are happening on those lanes at any given millisecond. And it's genuinely fascinating how much power a single pin holds here. Take the M/IO pin, for instance. This single output instantly switches the entire system's focus. When it outputs a 1, the whole computer knows the processor is doing a memory operation. When it drops to a 0, the system knows it's talking to an input/output device. Literally one pin dictating two massively different directions. And once we know the destination, we need the action.
RD and WR are active low pins, meaning they trigger when the voltage drops to 0, and they tell the system whether the processor wants to read or write data. We've also got DEN to enable external data transceivers, and DT/R, which acts as a directional sign. A 1 means the processor is transmitting data, and a 0 means it's receiving it.
Oh, and we definitely can't forget the ready pin. You see, the 8086 is incredibly fast, but sometimes external memory devices, well, they're pretty slow. So the ready pin politely forces the fast processor to enter a wait state if its value is 0. It essentially just pauses the factory line until the slower memory can catch up and flip ready back to a 1. This is absolutely crucial for preventing system errors and missing data. Which brings us to Section 4, Emergency Alarms and Interrupt Signals. Now, you might be wondering, how does this tightly scheduled system manage sudden, unscheduled external emergencies? Well, it turns out the 8086 has pins dedicated entirely to system alarms. First up is INTR, the standard interrupt request. Now, this one is maskable, which is really just a fancy way of saying the processor can choose to ignore it if it's currently busy doing something more important. But contrast that with the NMI pin. NMI stands for non-maskable interrupt. This is the absolute highest priority alarm, and it literally cannot be disabled. If the NMI pin gets triggered, which is usually by a catastrophic event, like an impending power failure, the processor forces absolutely everything else to a halt so it can handle the emergency immediately.
Now, when the processor actually does accept a standard acceptable interruption from that INTR pin, it has to formally reply. It does this using the INTA, or Interrupt Acknowledge pin. It's essentially saying, "Hey, I hear you, I'm ready." We also have the test pin, which is actually quite unique. The processor uses this pin in conjunction with a wait instruction to literally pause execution entirely. It just sits there and waits until external hardware sets the test pin back to a 1.
All right, Section 5, Minimum versus Maximum Mode Foreman. This covers what is arguably the most fascinating feature of the entire 8086, its ability to completely alter its own architectural identity. So the crucial point here is how wiring just one single mode selection pin, the MN/MX pin, transforms the entire chip. If you wire this pin to a 1, the 8086 enters minimum mode. In this mode, it operates as a solo worker in a single processor system, and it manages bus control simply by using the basic hold and HLDA, or hold acknowledge pins. But if you wire it to a 0, it enters maximum mode, and suddenly the 8086 transforms into an advanced foreman in a complex multiprocessor environment. This completely changes the physical function of several of its pins to allow for much more advanced delegation. In maximum mode, specific pins undergo a complete transformation. For instance, we get the lock pin, which the 8086 triggers to physically prevent any other processor from accessing the bus. It's literally a do not disturb sign for critical instructions. We get QS0 and QS1, broadcasting the internal status of the instruction queue. And remember those simple hold and HLDA pins from minimum mode? Well, they're replaced by RQ/GT0 and RQ/GT1, which are bidirectional pins that allow complex coprocessors to negotiate for bus control. Finally, pins S0, S1, and S2 become vital status outputs. Because the 8086 is acting as a really busy foreman in this mode, it offloads complex signal generation to an external 8028 bus controller, and it uses these S pins to tell the controller exactly what kind of bus cycle is currently happening. Finally, Section 6, the 40-pin architectural legacy. Let's just take a step back and look at the incredible big picture of what this extreme physical constraint forced the Intel engineers to achieve. Putting it all together, it is just incredible how much immense capability was squeezed into this tiny, tiny footprint. We've got our multiplexed shipping lanes, our traffic light control pins directing the flow, emergency interrupts standing by, base utilities keeping the factory running, and of course, that brilliant dual mode adaptability. Every single one of those 40 pins had a specific, absolutely vital role. There was literally zero waste. Through these ingenious hacks, Intel engineers laid down the exact x86 architectural foundation that literally dominates global computing today.